All right, everybody, welcome in. Welcome back to your favorite class. Yes. All right, I appreciate your pun there, Mr. Rogers. These jokes are leaving me winded. Grumble, grumble. Okay. Right. Announcements. Homework number 3 due tomorrow. That's on short fiber and particulate stuff that we sort of talked about last week. So make sure you get that in by 4 o'clock, beginning of lecture. Also, your manufacturing breath assignment is due on this Thursday. So we've talked about that for quite some time now. Hopefully, you had a chance to take a look at that. I'm not looking for, like the most detailed, amazing document, though. If you want to do that, that'd be nice. Just give me some overviews of the process, describe the process, give me a couple examples of what's made with that, and that's sufficient. Just enough to like dive in and tell me that you just have the basics for each one of these things and sort of how they differ. It's kind of what I'm looking for. All right. Last announcement I want to make is that your first exam for the class will take place next Thursday. I'll have a little bit more about this in a more formal handout in just a bit, but I'm going to hold the exam virtually on Teams, so please do not come to the lecture class next Thursday. Everyone just take the exam basically at your house or wherever you normally like watch the lecture virtually is probably best. And the idea is I will release the exam right at 4 o'clock. You'll have 50 minutes to do the exam, kind of, in the space in front of you. You won't have to like copy down the question or anything. Just get a piece of paper and some pencils in front of you and go to town on the exam. When you're done with that 50 minutes, take a picture of it, send it to me by email, just like you would normally submit homework, and that'll be it. So that's kind of how the exam is going to go. More formal details to come. Question. Is school open on Monday? I think we have school, yeah. I didn't know it was Columbus Day. I'm ignorant, as they say. I'm ignorant. Okay. Yeah, school on Monday as far as I know. Right. Indigenous Peoples Day, says Cristiano. Okay, cool. Any questions for now? You at home or you in the audience? Okay. If there are no questions, then let's kind of pick up where we left off. And where we left off, we were discussing anisotropic materials. And what we were really doing is kind of digging into the nitty-gritty, the mathy details about how we might fully define a material that isn't necessarily isotropic. Okay, so let's sort of pick up where we left off with that. And to fully do this, we had to sort of initiate ourselves into indicial notation, which is something that we're going to utilize a little bit here. And so let's kind of do a recap of where we learned last time. So anisotropic materials. And so last time we talked briefly about indicial notation. We gave some definitions. I'll kind of scroll over those, but last time generally we had indicial notation. Where that looks something like sigma ij. You've probably seen something like this before, and this is useful in representing multiple stress states. Okay, so this, if I and j go from 1 to 3, then this is 9 stress states. For, sigma 1, 1, sigma 1, 2, sigma 1, 3, et cetera, et cetera, et cetera. Okay, we all sort of understand that. We said that if we had some general things that we could also describe, things like the identity matrix, which we called the Kronecker delta as delta ij, then you could do some tricky little things here to actually represent Hooke's law using this sort of like indicial notation. Or if you wanted to say represent the stresses in terms of the strains, you might write something like sigma ij, which is 9 stress states, is lambda times the trace, I'll write it as TR, of epsilon ij, where epsilon ij is the 9 strain states, multiplied by the Kronecker delta ij, plus 2g epsilon ij. right? This is just like a shorthand version of Hooke's law, and this here is actually 9 equations. This is for an isotropic material. This is actually 9 equations. All right. So we kind of went through an exercise last time where we showed if you do like sigma 1, 2, how does that simplify into the Hooke's equation that you really know? And just to remind you that lambda here is a material parameter known as the Lemay parameter. The lame parameter? No, it's Lemay. Some snooty French dude, I guess. Ha ha, my name is Lemay. Ha ha. I have parameters. Ha ha. Where this is just kind of a combination of material properties that you are probably more familiar with. All right. All right, cool, great. So that's just kind of showing why additional notation is important. All right. We said though, in general, we could sort of minimize this, right? So in additional notation, what you see here, this is like 9 equations. But we generally know that if a material is obeying conservation of angular momentum, that we could say that sigma ij is equal to sigma ji. And instead of writing this as like a 3x3 matrix, maybe we want to write it as a 6x1. Okay, so we move to contracted additional notation with things like sigma ij equals sigma ji, and with strains epsilon ij equals epsilon ji. Make sure my volume's up here. Okay, good. Both of these guys rely on conservation of angular momentum. I can hear the pounding at the construction yard away here as well again today. That's very exciting. Working hard on that construction. All right, so if we want to utilize this idea, then we go from what would be like the 9 strain states in that 3x3 matrix to actually 6 stress and strain states. Which we just represent with like sigma capital I, where I goes from 1 to 6. And so what you want to sort of think about in your head is this is like sigma 1, 1, sigma 2, 2, sigma 3, sigma 2, 3. Sigma 1, 3, sigma 1, 2. Sorry about the matrix there. Let's make it more beautiful. Sounds like someone has their mic unmuted. Can you please mute your microphone? Or what we're labeling generally as sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and sigma 6. All right. This is like our contracted additional notation for the stress. Right. Similar for strain. And we'll usually label this as like epsilon j, or j going from 1 to 6. The same sort of like general structure as over here. So when we have this sort of like contracted additional notation to represent these like 6 stress states, then we can write a general Hooke's law that relates the stress to the strain in the most general way possible. that might look something that is simply like sigma capital I is equal to capital C I j times epsilon j. This is the most simplistic form, where this capital Cij, this is the stiffness matrix. And it's a 6 by 6 here. Or you might see it the other way. The strain's written in terms of the stresses, where this Sij is the compliance matrix, which is again 6 by 6. Anybody taken like the computational FEA class or whatever? I don't know how many of those. What do you call it? Like FEA class? Is it just computational mechanics class? I don't really know what you guys what they call it here, but if you're taking a computational mechanics class, this might look familiar to you. This general like 6 by 6 stiffness matrix. It's kind of the basis for how most FEA softwares actually work. Okay. All right. Why they use capital C as the stiffness matrix and capital S is the compliance matrix? I think it's kind of funny. The capital letter C is stiffness. The capital letter S is compliant. Whoever did that, I don't know. They were smoking something. I don't know. But it is what it is. Okay, so let's now move through it and take a look at this bad boy and talk about kind of what's going on with this particular guy. So let's take a look at this stiffness matrix in a little more detail. This capital Cij. So this is more or less a 6 by 6 matrix that contains all of the material constants associated with your material. Okay. Now we're going to make one more simplification here, which is we're going to assume that the materials that we deal with in this class are what's known as Cauchy elastic materials. This is well beyond what you need to understand for this class. This is like graduate level mechanics, but let's just put this here for good measure. And I'll explain what that means. So in this class, we will assume that Cij is symmetric, and also Sij is symmetric. So what do I mean by that? That means that the stiffness matrix Cij is equal to Cji, and Sij is equal to Sji. It's very similar to like how the stresses and strains have like their 3 by 3 matrices, and we just say that by conservation of momentum, the matrices are symmetric. We have the same idea. We're going to assume that these stiffness matrices and compliance matrices are also symmetric about their diagonal. And this is probably beyond this class, but this is true for Cauchy elastic materials. Okay. You want to be scared? Go Wikipedia Cauchy elastic materials. Okay. Or you want to be even more scared, Google green Cauchy elastic materials. Then you'll be really scared. Okay, but Cauchy elastic materials only if you want to be like moderately scaled. I mean, it is October after all. Let's be a little spooky and get a little scared. It's like October time, all right? So it's true for Cauchy elastic materials. I'm not going to ask you to understand this or know this. Just understand that most materials have this general behavior. Okay, so my point is then for any general material which is Cauchy elastic and obeys conservation of angular momentum. That's 99.9% of materials on Earth. Then the stiffness in compliance matrices will have 21 independent entries. Okay. So if you have any general anisotropic material that is Cauchy elastic and obeys conservation of angular momentum, you need 21 material constants to fully define that piece. Okay. So when we talk about composites having like E1, E2, E3, new 1, 2, new 2, 3, new 1, 3, G1, 2, G2, 3, G1, 3, all these things, these are all values that are feeding into this stiffness matrix more or less. Okay. So if you think of some general material, you would need 21 of those constants that looked like that to populate this matrix fully. All right. We're going to try to whittle this down. All right. So you want to see this kind of in practice. I'm just going to pull pictures in here since I don't want to write this down, but this kind of comes from the notes. And you may consider like making some shortened form of this if you're like writing by hand, just so you see visually like what this matrix looks like. I think it's sort of an important thing. All right. So here's your general stiffness matrix that you might consider. This is like sigma 1 equals C I J epsilon J. This is Hooke's law here. So when I say that sort of this 21 material constants are required, yeah, we need 21 independent things to sort of populate this triangular portion of the stiffness matrix in this upper diagonal. Okay. So given some stress state at some point and some resulting strain state at some point, you can relate those things together through this stiffness matrix capital Cij. All right. Generally, 21 independent entries required. Now, question for the audience. How many independent elastic constants are required to define an isotropic material? Anyone? Lay it on me. Which three? Okay. We have a guess from the audience that is E, nu, and G. But I would argue that G is not independent of E and nu. Understand why that is? So we can write things like G is E on 2 times 1 minus nu, right? Okay. So in general, to define an isotropic material, you only need 2 material constants. So an example might be your elastic modulus E and your Poisson's ratio nu. Another example might be the Malomé parameter lambda and the shear modulus G. All right. Any sort of 2 material parameters like that are independent can be used to define an isotropic material. So the question then is, if you have an isotropic material and you have to populate what would be like the stiffness matrix here for that isotropic material, what would that actually look like? And let's talk about that now. So for an isotropic material, we need 2 material properties to fully define Cij. And I'll just say you can pick 2 of what you commonly know, like the elastic modulus, Poisson's ratio, shear modulus G. This Lemay parameter, lambda, is one. The bulk modulus, capital K, is also one that's sometimes used. But the point is that any two of these parameters can be written in terms of any other two parameters if you know the appropriate transformation. All right. So two of these values can be utilized to sort of fully define the material properties of your isotropic material. Okay. So if you select lambda and G, then Cij becomes the following. And I'm just going to write this out here because, useful. Okay. Lambda plus 2G. Lambda, da, 0, 0, 0. That's what you all were thinking, right? Two G or not 2G? No, I think the big thing is 5G these days. And then zeros, rest of the way here. And then we have G, G, G. All right, this is your 6x6 stiffness matrix written in terms of material constants G, the shear modulus, and lambda, the Lemay parameter, which I sort of defined before. Okay. So the point is that we can go from generally 21 material constants that you might need for a generally anisotropic material, wood, okay, and reduce that down to 2 independent material constants that are required to fully define, let's say, aluminum. And we've sort of alluded to how we're going to do this, but I want to mathematically show what an isotropic stiffness matrix looks like first before we get into it. But the way that we're going to do it is we're going to utilize planes of symmetry, planes of isotropy, to say, like, okay, if I've defined the stiffness in this direction, that means I only need that one variable to define the stiffness in all these other directions because of this isotropy or symmetry that we have. Okay? So here's your general stiffness matrix for an isotropic material. So we hear only 2 independent constants. And that is specifically G and lambda, but could be written in terms of others, like E and nu, right? Or others. E, nu, etc., etc., etc. Okay. So how do we go from that like most general condition to the isotropic condition? All right. Well, we do that by using planes of symmetry and planes of isotropy. And the answer here is planes of symmetry and isotropy. Handwriting. Okay. So remember we kind of defined what these things are: planes of symmetry and planes of isotropy. Don't want to beat that to death, but generally plane of symmetry, 180-degree rotation about the axis running through the plane. If that leaves the constants unchanged, that's a plane of symmetry. Plane of isotropy is one in which, regardless of the direction you load in the plane, you have the same material properties. Okay, so let's just remind ourselves what these things are with an example. And I'm not going to try to draw this, but there's a picture of this in your notes. And this is the general idea you should have in your head for like a unidirectional material. Should look something like that. Okay. Oh, got an itch in my nose. I don't want to take my mask down. Danger. All right. So this is kind of like the picture you should have in your head for like a generally isotropic material. All these fibers just like running in this one direction. All right. And, maybe that's what I should do for my lecture lobby going forward. Just play all One Direction songs. How would you guys feel about that? No one's going to come to my online lectures anymore. All right. So the unidirectional composite looks something like that. So if you look down the one direction, you see this. Here, which is like this. The 2-3 plane, you have this plane of isotropy. And that is that the modulus in the 2 direction approximately equal to the modulus in the 3 direction, approximately equal to the modulus in this direction, 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 and wait for it, this direction. Okay? So you get the idea. Regardless of how I sort of like load this particular plane, the modulus in the 2 direction equals the modulus in the 3 direction. I think that's pretty easy to see. This is a plane of isotropy. But if I look at some of those other planes, like let's say the 1-2 plane or the 1-3 plane, you're not going to quite see the same thing or quite have the same response. Right? Oh, I missed my one. No. Not my gumdrop buttons. What movie? Anyone? Not my gumdrop buttons. Shrek. All right, good. Best movie ever, except for like 50,000 other movies. Okay, but here, yes, this is a plane of isotropy, right? Regardless of how it's loaded, we got the same properties. This guy here, not plane of isotropy. Because, yeah, okay, if I load it this way or this way, it's going to behave the same. But if I load it this way, it's not going to behave the same as if I load it this way, right? So not a plane of isotropy. But it is a plane of symmetry. And that's because of 180-degree rotation of this guy about the 3-axis would sort of leave the material properties unchanged. Okay, so what does this sort of mean mathematically? All right, well, how are we going to attack this sort of problem to look at simplifying that stiffness matrix mathematically? All right, so in English, we'd say, for plane of isotropy, same behavior, all directions. But in math language, you would generally write it as the modulus at, let's say, theta equals 0. So if you thought about some rotation angle that you might want to consider, like let's say this is our particular axis, and let's do it on our isotropic piece. Our axis of interest, and we're looking at some angle here, theta. Then we'd say in math language that like the stiffness or the modulus of the material at 0 is the same as the modulus at the angle of theta equals theta, which is any arbitrary angle. Okay? Or you might just see it as the modulus at some angle theta. Okay, so with our little picture here, here's some coordinate system. We're just slapping right in the middle there. Just slap it right on there. Slap it a base. Okay? All right, this should be like the 2, 3. Then we'd say that, all right, if I just define this as like the angle theta equals 0, like normal, and I have some arbitrary other loading in this direction at some angle here of theta, then I would say that the modulus at theta equals 0 is the same as the modulus at theta equals theta. All right. That's what it would mean to be a plane of isotropy in terms of sort of like language that we just understand. So if we're going to mathematically talk about moduli and disorientation, moduli, then the way that we want to simplify the stiffness matrix is we want to say something like, okay, we have a stiffness or some sort of response of our material in disorientation. Now, what happens if we're in a stress state that's slightly rotated from that, let's say 180 degrees? Okay, so we rotate our stress element. You guys remember your stress elements from 2004? Okay, you got the stress element. You do a stress transformation to that stress element and rotate it to a condition of 180 degrees. And you would say, all right, if I'm on a plane of symmetry, then I know the stiffness matrix for my original condition should be equal to the stiffness matrix of my new 180 degree rotated condition. All right, you equate those things together, see what things match, what things don't, and you can sort of like simplify things out. Okay, so the way that we're going to sort of work through this is we're going to do transformations or rotations of our stiffnesses with arbitrary angles and see sort of how these stiffness matrices shake up. So again, we got a little bit more for our math precursors coming here, and specifically that is change of basis, or you guys might call a rotation. So we needed to do a review here quick of change of basis. Or what we might call rotations between coordinate systems. Right. You guys take that vector analysis class? You guys like talk about change of bases in that class? Like more than you care to talk about ever again, or not? You guys don't talk. You guys didn't talk about change of bases in your vector analysis class? Are you serious? Oh, okay. So maybe some of you did, maybe some of you didn't. That would blow my mind. I mean, that's like seems like would be day 1 or 2 or 3 in vector analysis. But okay, what do I know? Okay, so let's do this or motivate this with an example. All right, so rotating between like little x, little y coordinate system to cap x, cap y coordinate system. So we'll just review coordinate transformations. All right. So what you want to think of here pictorially, say you have x, y, and you're interested in what's going on in your new basis system, capital X, capital Y. Yes? And I have some vector out in space that I'm talking about or caring about. For us, that's going to be a stress vector, but for here, let's just label that vector as Q. All right, some vector out in space. All right. So XY as unit vectors. IJ, cap X, cap Y as unit vectors, capital I, capital J, right? This is like hearkening back to your statics days, possibly. Okay. Yeah, you guys are getting scared. They're crying in the audience. You should see them here. They're crying. Crying in excitement. Okay, if you have this situation, you could write that vector Q in either basis. All right, you could write it in little x, little y, or you could write it in cap x, cap y, using things like little I, little j, or cap I, cap j. All right, so vector Q. For those of you that have not had me before, I put bars over the top of my variables if they are vector quantities, just because I can't like write them in bold on the board. Okay, so vector Q can be defined in either coordinate system. For instance, it could be Q little x y plus Q little y capital J, right? Where if this is sort of like your general idea, then the triangle that you should have in your head is like this triangle here. Where this is QX and this is QY. You feel? All right. You could also do it in the other coordinate system. Q cap X cap I hat plus Q cap Y cap J hat. The triangle you should have in your head in this situation is this triangle here. Okay? It's the same vector in both situations. We can all agree on that, yes? Now, how we represent it in space is different depending on the coordinate system that we use, but the point is it's the same in both coordinate systems. So if I want to transform between, and let's put some distinguishing characteristics on here. Let's call it little x, little y to cap x, cap y. Then I can use kind of the following transformation. And that is like, let's say I want q little x, q little y. Written in terms of q big X, q big Y. All right. Well, it's going to be like cosine theta, sine theta, negative sine theta, cosine theta, multiplied by q cap X, q cap Y. This is your general transformation. Okay. And that is because you have transformations that look like this little I, which can be written in terms of cap I and cap J. So this would be like cosine theta, cap I plus sine theta cap j. And this is kind of like intuitive from the picture, right? So I want to write little I, which is more or less this portion of this coordinate system, in terms of cap I and cap j. Oh, this is backwards. Sorry about this. I wanted to do this for simplicity, sorry. Not much changed yet, just making this my more standard cap x, cap y. Sorry about that. I want to be consistent with the notes. So I write this portion of this coordinate system, which is like your little I hat, would be cosine cap I hat sine theta cap j hat, right? It's just like resolving this vector into this coordinate system here or this coordinate system here using sine or theta or cosine theta appropriately, where this is your angle of theta. You might have little j, negative sine theta cap I hat plus cosine theta cap j hat, okay? That's like writing this guy here in terms of this and this. All right, so you get the general idea. This information in to the little I here. This information into the little j here. I would come up with something that looks a lot like this transformation here. Okay? Writing the vector in one basis in terms of the vectors of the other using these sine and cosine rotations. All right, I could go the other way. To write it in the original coordinate system, given information about this particular vector in our sort of rotated coordinate system. In shorthand, this might be written as something like q little x little y is equal to this transformation matrix A. I'll put 2 bars on it so we know it's a matrix. It goes from cap x to little x multiplied by q cap x cap y. These things are like equivalent. I'm just sort of shorthanding them. And this is like q cap x cap y equals, let's call this b, which goes from like this little coordinate system to the big coordinate system, multiplied by q in the original unrotated coordinate system. We would call this A and this B matrix transformation matrices, right? Matrices which allow us to go from one set of basis vectors, like a little I, little j, to another set of basis vectors, which is like big I, big J. Okay? Hopefully we're good on this. One thing we'll also note for these transformations is the inverse of A is equal to this B matrix. Okay, so we're going from one coordinate system to the next. That's the whole point. All right. So what we're going to do is we're going to apply this to a set of material constants in one coordinate system for our general anisotropic material. Then say that it has a plane of symmetry, that if we rotate this guy 180 degrees through this transformation that we're about to come up with, the properties remain the same, right? So we'll have some stiffness matrix, multiply it by some transformation, and say that after we multiply by transformation, we'll have the same properties if we're on a plane of symmetry or plane of isotropy. Okay. But we're not doing this in 2D. We're doing this in 3D. The example I just had there was in 2D, sort of a motivation. But we can think of the same sort of idea for our 3D system by considering our contracted notation for the stresses, multiplying it by an associated transformation matrix to get it into some other coordinate system. Okay, so let's look at what this looks like in 3D. This will be it for today. Let's get through this. Here's our 1, 2, 3. And let's say we want to move to some other coordinate system that's like x, y, z. ABC, easy as x, y, z, or something like that. We can define some angles here. Let's define like this angle here as theta x1. It's the angle that exists between the x-axis and the y-axis. Similar idea here, it's just theta x2. It's the angle between the x-axis and the 2-axis. Here is theta x3, exists between the x-axis and the 3-axis. You could also do this for y1, y2, y3, z1, z2, z3. Okay, so let's assume 1, 2, 3 coordinate system is in material coordinate system. What do I mean by that? Well, usually the one direction is the direction of the fibers, so we'll assume 1, 2, 3 is like our normal definition. And then x, y, z is arbitrary coordinate system. Maybe that happens to be the coordinate system of the loading that we're in, right? Loading this in some arbitrary general fashion. That might be something that we have. If we wish to know stress state in 1, 2, 3 coordinate system, which is maybe where we know all our material properties, right? The 1, 2, 3 coordinate system is generally what we would probably understand and know about our material. Then we transform with a transformation matrix, which might generally look like, here's your stress state in like the 1, 2, 3 coordinate system. Transformation matrix T cap I cap J, sometimes written as T lowercase I lowercase j, multiplied by the stress state that you have in the x, y, z coordinate system. Fully blown. So we see it. You might see this, or let's write it the other way, abbreviated. Let's do Here's your full stress state in your principal coordinate system, your material coordinate system. This might be, we'll just call it for now, Tij. This is a 6x6 multiplied by whatever stress state you have in the XYZ coordinate system. Okay. There you go. All right, that'll be it. Preview on your transformation matrix. Yikes. This is what it is. We'll talk about this next time. That's it for today. Thank you. Lucas put a picture of the of the gingerbread man from Shrek in the chat. You monster! The best exchange in that movie is when they're saying, "Do you know the Muffin Man? The Muffin Man? The Muffin Man, who lives on Drury Lane?" It's too good. Ah, there's a second drawer. Okay. Yeah, sure. Let me stop the recording here quick.